positive now. You don't know that.
What limits is that? Is it the...
It's Ubuntu.
Oh, Ubuntu, yeah. That's things. I have a defiance.
Oh, Debenham, yeah.
Yeah, I don't know.
Yeah. Well, Linux or Ubuntu is Debenham based though, isn't it?
I think so. Yeah.
I think, yeah. Okay, let's see. So, workbook and slides, physics, mechanics, and we're now on 50. Okay. So not too much in this lecture now. We've been doing kind of complicated stuff. But the good news is actually this particular lecture, it gives us a theorem which can help us in certain problems involving turning force. So if you can write this one down, Lami's three-force theorem is what we're going to have a look at. Yeah? Got that? Okay. Yeah? See what has that? Yeah. Okay. Right, so this particular type of problem is actually a very special type of problem. We had a look at a problem like this last time, didn't we? We did the ladder up against the wall. But these types of problems in physics, there's actually a little trick to solving them that makes them much easier than what we did last time. And it only works for these types of problems. And what's so special about this type of problem, the reason this one's important is because of two things. Number one, there's three forces acting on it. So you can see there's the reaction with the wall, the weight of the ladder, and the reaction with the ground down below. Okay? And why did we say that this one was perpendicular last time instead of being at an angle? What made this different to this one? Do you remember? Why was this perpendicular? What was it about the wall that made this one perpendicular?
Rough.
Well, this one was smooth and that one was rough. Yeah. So if it's smooth, it's perpendicular, and if it was rough, because of the friction, it's at an angle. Okay. So number one, it has three forces, and number two, it's an equilibrium. If you have those two things, there's a trick to help you out here. So I think you should at least make note that the type of problems we're looking at today are problems where there are three forces and it's an equilibrium. Okay, so this is a special type of problem. So can you make note of that? Three forces and an equilibrium. So that's what we need in Lami's theorem. You could even draw the picture for an example if you want with the three forces on it. Okay, did you write that down?
Don't.
Let me just see what I have on the next one. Yeah. Now there's something I drew in the picture I want you to notice about the forces. Do you see that I put a dotted line where the forces point? So you can see here, this one, the weight acts down. You can see there's a dotted line here. This one here has a dotted line. And this one here has a dotted line. What do you notice about those three action lines? They do something. They meet, yeah. They meet at one point. Now they didn't have to do that. You know, it could have been like this. Like you could have had something like let's see, just get the pen here. What the heck is wrong with this? Weird. What the heck? It's never happened before. Anyway, actually, it's actually alright, because I actually do need to draw straight lines. So it could have been like this. The three forces, they might not have necessarily met, you know. But what Lami discovered is that when you have three forces in equilibrium, they all must meet at one point. So his theorem, when three forces act in the same plane on a mass in equilibrium, then all the lines of action meet at one common point. This is the theorem. Got that? So, the proof I won't really do. It's a very short proof, but it's not necessary. The sum total of the proof is that it only works when there's three. So in fact, if you have four forces, then there's no rule that says they all have to meet. It's only actually when there's three. It might seem a little bit strange. Anyways, the other thing I want to show you is there's actually another way to state this theorem. You can actually say it as a formula as well, which is also useful. So, when you have three forces, F1, F2, and F3, and they act at a single point in equilibrium, then you have this F1 over sine theta 1 equals F2 over sine theta. Now actually, before you actually write that down, I just want to go back to the picture to show you what the F's are. So when I say F1, F2, F3, I'd mean F1, F2, F3, for example. And the angles that I refer to are, if you can see this, actually, you know what? I'll draw it in a moment. I'll just let you write it down. It's the angles where they meet, but I'll draw it in a moment. You can first just write it down. So you have F1 over sine theta 1 equals F2 over sine theta 2, and F3 is sine F3 over sine theta 3. Theta 1 is the angle between F2 and 3, theta 2 is the angle between 3 and 1, and theta 3 is the angle between 1 and 2. Should kind of remind you of a formula from trigonometry, if you remember from high school.
Yeah, but
but it looks like a trigonometry formula, doesn't it?
yeah.
Do you know which one? Anybody? If you remember. Yeah. What's the name of this formula? That's the one, all right. Do you want to know what the name of the formula is? It's called the sine rule. You don't have to write all this down at the bottom because you can just draw it, okay? So I need to figure out why my pen is doing this. I don't know what's happening here. I put it. I put in some weird kind of mode, didn't I? Brush, change brush, brush group, classic, pencil. I must have something turned on that I can't see. But what?
I think that was it.
Oh, it was this?
I think that's right. No.
It's a bit better. No, it's back.
Because it says down there,
draw straight line, shift, add curves, control. Oh yeah. So I want to turn this off. Whoa. Draw straight lines. I don't want to draw straight lines. Change brush. Yeah, that's what I thought. I haven't set the pen.
There are arrows at the top.
Experimental. How? Ah, you know what? I'll just reopen the program.
Wait. Try now.
What? That makes no sense. Alright, so now I can. It heard that I was going to close it, I guess. What we have is, we have our object and we have the three forces acting on it. So there is F1, and we know that they're all supposed to meet, so we'll put F2 here, and we'll put F3 here. So Lami said that F3 divided by, this is the angle here. This is what we call theta 3. It's the angle between 1 and 2, the angle opposite the 3 force. This one here, this one is theta 2, and this one here, theta 1. Okay, so Lami gave us a formula for relating the forces with the angle. Very useful, actually. So if you want, you can draw this instead of writing the last paragraph down. Okay, so this is what it looks like for the formula. Okay, you drew that? Yeah. Right, so, I drew the last one. So let's actually have a look at Lami's theorem in action. So a 10 kilogram ball of radius 5 centimeters hangs on a smooth wall by means of 8 centimeter string, which is attached to the wall. Find the tension in the string. So you have 10 kilogram, 5 centimeters, and 8 centimeters. So this is what the picture looks like. You've got a wall here, and on the wall we have this hanging. And what did I say this was? This was 10 kilograms. And the radius here is 5 centimeters. 5 centimeters. Okay? And there's a string attached between the ball and the wall. So it's almost like a door knocker. You pull it out like that. Okay, and believe it or not, what else? Oh yeah, we know the length of the string is 8 centimeters of string. So believe it or not, that is enough information to work out the tension in the string. First, let's draw the forces. So how many forces are here?
3.
Well, it's going to be 3, yeah. So what are they? What's the first force? Yeah, so I'll put in black here the weight, which will be 10G. Right, what's the other force? The string, yeah. So that there is the tension. And what's the other force on the ball?
To the right.
To the right, which is called the reaction force. Now this one is perpendicular because the wall is smooth. Alright? If I was to draw a dotted line here, they obviously meet in the center of the circle. But according to Lami, this third force also must meet in the center. Now that's really useful, because if you didn't know that, you have no idea what this angle is. No idea. Because you might think, well, can't I just attach it here? Couldn't I attach it here? Like, there's many choices. No. Lami said that this one has to point to the center as well. Okay, that's really useful, because that means we can now work out the angle here. So if I was to draw this triangle here, I know that this side is 13 centimeters. How do I know that? If I'm looking at this triangle here, how do I know this is the 13?
Yeah, the radius and the...
Yeah, that's it. The radius, the 8 and the 5. Right, how big is this side? 5. Okay, well, how can I get this side? Pythagoras. So I'll get 12. So can I know this angle? I can. Right, so just for the moment I'll just call that angle theta. We can work it out in a minute. So let's take the t here. Actually, I'll just draw it on this picture to make it less messy. There's the t. The t has two parts. This side and this side. Right, how big is this one? What's that one? T cos or sine? Cos theta. And this side? T sine theta. Yeah? Okay. So, two forces here, left and up. What does the up force equal? What's this one? The up one equal? T sine theta equals 10g, good. So what does t equal? 10g over sine theta. Do we know 10g? Of course we do. Do we know theta? We can. We'll just have to do theta is tan inverse 12 over 5. Yeah? Yes? Can we type in tan inverse 12 over 5? Sixty-seven point 38 degrees. So 98.1 divided by sine 67.38, what's that? About 50 newtons or something?
1.4. 106.
106 newtons, okay.
Oh.
Yeah?
Yes.
6.37. Yeah, 106.27, so 106. Yeah. Yeah. This is pretty useful, isn't it? Lami's theorem there. You could have used the other formula as well. If you worked out the angles as well, you could have used the other formula. If I was to just, can I scroll down a little bit here? If I was just to draw this again, okay? Here's one force, and then the R force is like this, isn't it? And then the T force is like this. And what did you say this angle was? 67 is this angle. So if I add that to 90, that is 157. Yeah? 157 degrees. This angle here, how much is that? That's 90. And then this one here would be 360 minus 90 minus 157. Yeah? What's that? 113. So you could have said t over sine 90 equals r over sine 157 equals 10g over sine 113. Yes? So what's the useful one here? It's the first and the last. If you said that is equal to that. Because sine 90 is 1. So that's gone. So you could say t is 10g over sine 113, and that will be the same number as that. So you actually have, you can do it by thinking about it as a diagram or by actually using the formula. Okay, so Lami's formula is quite useful for these types of problems. I'll do another example. I'll just give you a minute to write this one down. We'll do another example. Yeah.
Can you explain one more time the triangle?
Oh, where did I get the numbers?
Yeah.
So the first, this string I tell you is 8, and this I tell you is 5. Yeah, enough said? Okay. So actually, if you want to split it up, I've kind of done this two ways. So that's the first way, and that's the second way, and they both give me the same answer. Now this is actually a good exam question. You don't get it often in the exam, maybe 1 in 5 exams, but my experience is that the question is usually overmarked. You get more marks than you really should for this type of problem. Nearly finished, and nearly got that. Has anyone seen this in physics before, this formula? Yeah. It's useful. It's a useful formula. Anda, you have it written down? Yeah. Lucas? Yeah. Hold it up the front here, guys. Okay. You can see okay, or there's something you need to check? No, it's okay. Alright, let's continue. Yeah? Which part are you at? Okay. Matt? You got it? You sure? I'll give you 10 more seconds. Your presentation was on electricity, wasn't it? Oh, waves, okay, yeah. And how did that go?
For us, it's
You guys were electricity, yeah. How was that one? Yeah. Did Connell ask you any questions afterwards? What did he ask you?
I don't remember.
Yeah. Do you remember yours?
Yeah,
I think
he asked me how much, because I spoke about wind turbines and solar panels, he asked me how much electricity would they produce, like for
he asked me if
you know,
how like
I
it's
didn't know.
related to matter.
Like how much electricity can they provide?
Okay.
Okay, wait, I remember. He asked her about the how the particles can behave, how waves can behave as particles in waves.
No,
That's what he asked her.
he asked me how it has to do with matter, and I told him that waves do not transport matter and the energy.
Ah. He knows something you don't know.
Really?
Yes, he does.
Well, that's
yeah.
what I found on the internet.
Yeah. Because there's an advanced topic which he's actually sat in on the presentation a couple of times. Because you have your active listening, and sometimes I do the active listening, and sometimes I do a physics topic. So there's a particular topic called quantum mechanics, and he's heard the presentation probably 4 or 5 times. So that's why he was asking you that, because that's what he knows about waves. So no, actually that's very interesting. So he had a little bit of information you didn't have. He'd be pleased with that when I tell him. Okay, let's continue then. Right, so 2 more examples to do. This one here is actually the one we did yesterday. It's the sign hanging up on the wall. So let's have a look at this.
So I don't need to draw it again.
Yes, we have to draw it again, although it's not going to be as complicated. So what length was that? That was 40 centimeters, wasn't it? And then the sign here, that was 20 centimeters. Isn't that it? Something like that. And this side here was 40. And then it was 2 kilograms. And oh yeah, this here it was like this, wasn't it? And this side here, that was also 40 centimeters, and this was the sign, and that was the beam. And my question is, let me just get a different colour here. What do I want to use? This one. The reaction force at the hinge. What is the direction, the angle? So you remember that there's 3 forces here. The first one, you can't really see the difference there. This type of blue. Right, the first one here, the tension. Okay. Then we had the weight, and someone was asking me, well, why did I put it here? Yeah.
How long is that? Black arrow.
Oh, that's a 40. It's the length.
Oh.
Yeah. What I mean is from here to here is 40. This thing here. Now, who was asking me yesterday about the weight? So, like the weight is here, but you could put it here. Like, it doesn't really matter because it's just that it's downward weight in the middle. Okay. So I'll draw it here if you prefer. How big is that? 2G. 2G. Okay. Now, dot. You can work out this angle because we know how big this side is. What is it? It's 40. And we know how big this side is. It's 40. So how do we get this angle? Tan inverse 40 over 40, that will be 45 degrees. Okay, so we know that angle. Now these two meet here. So what does Lami tell us about the reaction force that's here? It should also meet right there. Now, how big is this side of the triangle? 20. Because it's in the middle. How big is this side? 20. This height is the same for both. So, oh no, we're not doing that yet. These are the same triangle. Yeah, this is isosceles, yeah. So what is this angle here? 45. And that has answered the first part. Is that the same answer we got last time? Or did we even calculate an angle when we did it? We didn't, okay. Oh, but we calculated the x and the y. So I'm willing to bet that the x and the y were the same number.
Sin 45, yeah, we did.
Yeah. And they have to be the same because the angle here I'm saying is 45. Yeah. So obviously this is a much easier way to get the angle than getting the two forces. Yeah. Okay, so the next part. What is the magnitude what is the magnitude of the reaction force? So now I want to know how big is this reaction force? Okay. So let's resolve. Here, horizontally, that is or cos 45, correct? And here vertically that's or sine 45. Right, what two equations can I make? So what are my total up forces in this? Oh, and sorry, this guy, that one is t cos 45, and this one here, t sine 45. Right, what are my total up forces here? Yeah, two of them, what are they? Or sine 45 plus t sine 45, what should that equal? 2g. Now let me just divide by the sine 45. So I end up with r plus t equals 2g sine 45. So this simplifies to 2 root 2g, whatever that is. Okay. Now, what are my forces going to the right here? What's my force going to the right here? T cos 45, what should that equal? R cos 45, right? What can I cancel here? So now I have the equation t equals r, and I also have this equation. So, what did I say I was looking for? I was looking for r. Alright, so if I put that guy in there, I'll get r plus r equals 2 root 2g, because t and r are the same. Yeah? Right, so 2r equals 2 root 2g. What can I cancel? Cancel the 2's. So I end up with my answer, r is root 2g, which is about 14 newtons or something. Oh yeah, what is it? Is it close. 13.8 newtons. Yeah, that sounds about right. Oh wait, that was the answer I got last time I did it, was it?
13.9.
Okay, 13.9 then. Yeah. Yeah. And lastly, what's the tension? What's the T? What's the tension force here?
R.
Yeah, it's R. And what's R? Yeah, so what's the T? A little bit easier this way, huh? Because I know you didn't like this question yesterday. A lot less work this way, isn't it?
Yeah.
Oh wait, you missed the lesson yesterday because you were sick.
I missed.
Ah, well, your classmates will tell you the way we did it yesterday was quite hard.
Okay.
Agreed? Yeah. Okay, if you can write this down.
Why is the reaction cost like this?
Ah, remember yesterday? So, it's connected to a hinge in the wall. The hinge is doing two things. It's holding it up so it's not falling, and it's also pushing it out. So if it's going up and out, it's then at an angle. Okay, do we have this written down? Not yet. Got this? Almost, okay. We'll do one more example now. Maybe the ladder next. Okay. Yeah. Let's have a look. Okay. Right, and this again is the same one we did yesterday. The 13 kilogram ladder of 13 meters against the wall. And my question is, what is the angle? So what angle did we get last time yesterday? I know we calculated that.
78.2.
Was Oh, you had to go to the bank.
Yeah.
How much work did it take to get that angle? How much paper did you use up? Half a page? 2 pages? 2 pages. All right. Let's see how we can do it using Lami's theorem. Okay, so let's do was it 2 pages for that question?
A half.
A page and a half. Okay.
Half page.
Oh, half a page. All right. Well, let's see what we can get. Right. Here's the ladder. This side we said was 5 meters. Yeah. And how big was the ladder? 13 meters. And therefore, what's this length here on the wall? 12 meters. Okay. Now, the weight. How big's the weight? Was 13 kilograms. So what's the weight? 13g. And then there's a reaction force. Yeah. So there's a reaction force here. What letter did I call that yesterday? S. Okay. So that goes across like that, and this goes up. Like that. So can you see that they meet right here? Therefore, according to Lami, where must this reaction force meet? It must also meet here. Yeah? Now have a look at this triangle, which I'll do it in green. How big is this side of the triangle? 12. Now, how big is this side? 2.5. So, how could I get this angle here, which I'll call theta? That'll be tan inverse 12 over 2.5. What is that? Calculate, please. 78.2 degrees. And what answer did we get yesterday, Siva? 78.2. A little bit shorter this way, huh? So I hope you appreciate the importance of his theorem. Yeah, you wrote that down? Yeah.
Yeah, I think we got that.
This lesson really continues from what we did the last lesson, so you're seeing it a little bit out of context, you know. I suppose the next lesson would have been better because it starts from a new topic, which is work, energy, power. Okay. Do we have this? Yeah. I don't think there's another example. Oh no, there is. Okay, one more example to do. Can I scroll down? Yeah. Okay, the last example. A 1 kilogram mass hangs from the ceiling by two strings, each making 30 and 40 degree angles with the ceiling. What's the tensions in the string? So you've got the ceiling here, you've got a mass here, it's 1 kilogram, and there's two strings holding it together, one here, one here. This one is at an angle of 30, this one here is at an angle of 40, and this is a 1 kilogram. So the force here is 1G, yeah. 1G. Now, I want to know what are the tensions in the string. So there's a tension here from that string. We'll call that one T. And there's a tension here. I can't quite get that drawn right. And there's a tension here. I'll call that one there S. Now, let's use Lami's formula. If that's 30 and that's 40, together that's 70. And since this is a triangle, how big should this angle be? 110, because the tree must make 180. Now, if that's 40, how big is this angle here? This little one here. How big is this angle? 40, yeah, it has to be the same as the one up here. So if that's 40 and this is 90, how much is this one? 40 and 90? 130. Now 110 and 130 is 240, but the total must be 360. So this is 120. So you can say, according to Lami, that 1G, which is 9.81, over sine 110 must equal S over sine what angle? What goes under this one? 120, good. That must equal T over sine 130. So you can put these together and say S must equal 9.81 times sine 120 over sine 110 equals, and T must equal 9.81 sine 130 over sine, am I looking at the wrong one? Sorry. T, oh yeah, no, same thing, sorry. And then we'll get those two, and then it's finished. First one, 9.04 newtons. So basically 8 newtons. I'll put it in 7.99 newtons then. So do you notice what was nice about this is we didn't need to resolve any of the vectors. We didn't need to use t cos, t sine, s cos, s sine. Okay, you wrote that down? Yeah?
I got that right, actually.
Oh, good. Okay. Yeah? Right, so let me just cross this now.